Welcome! In this session, we'll dive into problem number 376, titled Wiggle Subsequence. This problem challenges us to identify the longest subsequence in an array that alternates between increasing and decreasing. We'll explore multiple approaches to solve this, analyze their efficiencies, and uncover key insights along the way. Let's get started. A wiggle sequence is a sequence of numbers where the differences between consecutive elements alternate strictly between positive and negative. This means that if one difference is positive, the next must be negative, and so on. The sequence starts alternating from the first difference, which can be either positive or negative. For example, the sequence 1, 7, 4, 9, 2, 5 is a wiggle sequence because the differences alternate as follows: 6, 3, 5, 7, and 3. Notice how the signs of these differences strictly alternate. However, sequences like 1, 4, 7, 2, 5 are not wiggle sequences, as the differences 3 and 3 are consecutive positives. Similarly, 1, 7, 4, 5, 5 fails because the last two differences 0 and 1 do not alternate. The task is to find the length of the longest subsequence from a given array that satisfies this wiggle property. A subsequence is formed by removing some elements from the array without changing the order of the remaining elements. The input for this problem is an integer array called nums, which contains the sequence of numbers we are analyzing. Each element of the array is an integer, and the array can be of any length, from one element to a maximum of 10,000 elements. The output is a single integer representing the length of the longest wiggle subsequence within nums. Essentially, we need to determine how many elements can be included in such a subsequence while maintaining the wiggle pattern. To clarify, this doesn't mean altering the order of the array or inserting new numbers, it's about selecting elements that preserve the alternating positive and negative differences. In the first example, the input array is nums equals 1, 7, 4, 9, 2, 5. The output is 6, which corresponds to the length of the entire sequence. This is because the entire array already satisfies the wiggle property. Looking at the differences between consecutive elements, we see 6, up, 3, down, 5, up, 7, down, and 3, up. Since the differences alternate strictly between positive and negative, the entire sequence is valid. Therefore, the longest wiggle subsequence here includes all 6 elements, and the result is 6. In the second example, the input array is nums equals 1, 17, 5, 10, 13, 15, 10, 5, 16, 8. The output is 7, which represents the length of one possible wiggle subsequence. A valid subsequence is 1, 17, 10, 13, 10, 16, 8. If we compute the differences, we get 16, up, 7, down, 3, up, 3, down, 6, up, and 8, down. These differences alternate correctly, so this subsequence satisfies the wiggle property. It's important to note that there might be other valid wiggle subsequences of length 7, but we only need one to determine the result. In the third example, the input array is nums equals 1, 2, 3, 4, 5, 6, 7, 8, 9. The output is 2. Here, the sequence is strictly increasing, so the differences between consecutive elements are all positive. This means we can only include 2 elements in a valid wiggle subsequence, such as 1, 2, or 2, 3. Any longer subsequence would fail because the differences would no longer alternate. Therefore, the longest possible wiggle subsequence has a length of 2. This example highlights that, in cases of monotonic sequences, we are limited to choosing just one up or down step. There are several edge cases to consider for this problem. First, if the input array contains only one element, the result is simply 1 because a single element is trivially a wiggle sequence. Second, if all elements in the array are equal, like 5, 5, 5, 5, the result is also 1 because the differences are 0, so no alternating pattern can exist. Third, in strictly increasing or strictly decreasing sequences, such as 1, 2, 3, 4, or 4, 3, 2, 1, the result is 2 because only one up or down difference is possible. Lastly, since the array can have up to 10,000 elements, the solution must be efficient and handle large inputs within the given constraints. To start solving the wiggle subsequence problem, one approach we could consider is the brute force method. The intuition here is straightforward. We generate all possible subsequences of the given array and then check each subsequence to see if it satisfies the wiggle property, which means it alternates between positive and negative differences. Once we verify which subsequences are valid, we find the one with the maximum length. The steps for this method involve first enumerating all subsequences, then verifying each one for the wiggle condition, and finally tracking the maximum length among them. However, this approach has a significant downside. The time complexity is exponential, specifically, 2 to the power of n asterisk n, because generating all subsequences takes 2 to the power of n, and verifying each one takes n. Additionally, it requires n space during recursion. Given this inefficiency, especially for larger arrays, we do not choose this method as it's computationally infeasible. A better approach to solving the problem is using dynamic programming, which improves efficiency by building solutions incrementally. Here, we define two arrays, up and down. The up I array tracks the length of the longest wiggle subsequence ending at index I where the last difference is positive, and down I tracks the same length where the last difference is negative. The process starts by initializing both arrays to 1, since any single element is a valid wiggle subsequence. Then, for every pair of indices I and j, where j is less than I, we update these arrays based on the relationship between nums I and nums j. If nums I is greater than nums j, it means there's an upward wiggle, so we update up I to be the maximum of its current value or down j plus 1. Similarly, if nums I is less than nums j, we update down I. At the end, we return the maximum of the last values in the up and down arrays. This method is significantly more efficient than brute force, with a time complexity of n squared, due to the nested loops, and a space complexity of n, for storing the two arrays. While the dynamic programming method is an improvement, it still isn't optimal for larger inputs because of its n squared time complexity. To address this, we used the greedy approach, which is both simpler and more efficient. The key insight here is that we don't need to track the entire subsequence, just the relative changes between adjacent elements. Instead of using arrays, we use two variables, up and down, to track the lengths of the longest wiggle subsequences where the last difference is positive or negative, respectively. This simplifies the process. As we traverse the array, if nums I is greater than nums I1, we know it's an upward wiggle, so we increment up by setting it to down plus 1. If nums I is less than nums I1, we increment down by setting it to up plus 1. At the end of the traversal, the result is simply the maximum of up and down. This approach eliminates the need for nested loops and extra storage, making it far more efficient. The greedy approach stands out due to its efficiency. It achieves a time complexity of n, as we only traverse the array once, and a space complexity of 1, since it uses just two variables. This makes it ideal for handling larger inputs without any additional overhead. By focusing only on the relative changes between consecutive elements, we avoid unnecessary computations and storage, solving the problem directly and efficiently. Because of these advantages, we select the greedy approach as our strategy of choice. It combines simplicity with performance, ensuring optimal results for all input sizes while maintaining clarity and robustness. This makes it the most practical and effective solution for the wiggle subsequence problem. The problem we're tackling here is to find the length of the longest wiggle subsequence in a given array. A wiggle subsequence is a sequence where the differences between consecutive elements strictly alternate in sign. For example, if the first difference is positive, the next one must be negative, and so on. To solve this, we start with the brute force approach. The intuition behind this method is simple. We generate all possible subsequences of the input array, check which ones satisfy the wiggle property, and return the length of the longest one. The first step in this approach is to generate all possible subsequences. This can be achieved using recursion or backtracking, where for each array element, we decide whether to include it in the current subsequence or exclude it. Once all possible subsequences are generated, they are stored for further analysis. While this approach is straightforward, it lays the foundation for understanding the problem better before moving to optimized methods. Now that we have all possible subsequences, the next step is to check which of them satisfy the wiggle property. For each subsequence, we calculate the differences between consecutive elements and verify that these differences alternate in sign. If the first difference is positive, the next must be negative, and so on. If a subsequence meets this criterion, it is classified as a valid wiggle subsequence. To keep track of the result, we maintain a variable that stores the length of the longest valid subsequence encountered so far. Each time we find a valid subsequence, we compare its length to the current maximum and update the maximum if necessary. Finally, after processing all subsequences, we return the maximum length as the result. However, this brute force approach has significant computational overhead. Generating all subsequences requires 2 to the power of n operations, where n is the length of the array, and verifying the wiggle property for each subsequence adds additional complexity. As a result, the overall time complexity is approximately 2 to the power of n*n, making this method impractical for large input sizes. To better understand the problem and why the brute force approach is inefficient, let's delve into some key insights. First, the wiggle property is central to this problem. A valid wiggle subsequence must alternate in sign, and this property is what guides us in filtering the subsequences. Second, the process of generating all possible subsequences involves exponential growth as the size of the input array increases, which is why this approach quickly becomes infeasible for larger arrays. This exponential growth highlights the need for more efficient methods. Finally, the problem has an underlying recursive structure. The decision to include or exclude an element in a subsequence depends on whether it maintains the wiggle property with the previous elements. Recognizing this recursive nature helps pave the way for more optimized solutions, such as dynamic programming or greedy algorithms. To implement the brute force solution, we rely on a few key data structures. First, we use arrays to store the input sequence and any generated subsequences. Additionally, a list of lists is used to maintain all valid subsequences that meet the wiggle property. Finally, a single variable is used to track the length of the longest valid subsequence encountered so far. While this approach is functional, it can be optimized significantly. For instance, we can use pruning to stop generating subsequences early if the current sequence cannot possibly exceed the current maximum length. Furthermore, more advanced techniques like greedy algorithms or dynamic programming can reduce the computational complexity. These methods allow us to solve the problem in linear or quadratic time, eliminating the need for exponential enumeration. By leveraging these optimizations, we can achieve a solution that is both efficient and scalable. Lastly, let's consider a few edge cases that are important to handle in this problem. First, if all elements in the array are equal, the result is simply 1, as no alternating differences can exist in such a sequence. Similarly, for an array of length 1, the result is also 1, since a single element array is inherently a valid wiggle subsequence. Another interesting scenario is an array that already alternates between increasing and decreasing values. In this case, the entire array forms a valid wiggle subsequence, and its length is the solution. Addressing these edge cases ensures that our solution is robust and performs correctly for all possible inputs, regardless of their structure or size. The provided code solves the wiggle subsequence problem using an efficient greedy approach. The goal is to find the length of the longest subsequence where consecutive differences strictly alternate in sign. First, we handle edge cases where the input list has fewer than 2 elements. In such cases, the length of the wiggle subsequence is simply the size of the list itself. Next, we initialize 2 counters, up and down, to 1. These represent the lengths of the longest wiggle subsequences that end with an upward or downward movement, respectively. Initially, both are set to 1 because any single element can be considered the start of a wiggle subsequence. We then iterate through the array starting from the second element. For each element, we compare it with the previous one. If the current element is greater than the previous one, it creates an upward wiggle. In this case, we update the up counter to down +1 because the current upward movement depends on the length of the previous downward subsequence. If the current element is smaller than the previous one, it creates a downward wiggle. We update the down counter to up +1 for similar reasons. Finally, the result is the maximum of the up and down counters, as the longest wiggle subsequence could end with either an upward or downward movement. This approach runs in O(n) time and uses O(1) space, making it highly efficient for this problem. This is the Java implementation for the wiggle subsequence problem, mirroring the logic of the Python solution. We use two counters, up and down, to track the length of the longest wiggle subsequence, either ending with an up or down movement. Key differences include type declarations for variables and the use of Java's math.max for the final result. The code handles edge cases for small input sizes and efficiently calculates the result in O(n) time. To begin solving the problem, we are given the input array nums equals 1, 7, 4, 9, 2, 5. The first step is to check the length of the array. Since its length is greater than or equal to 2, we proceed with the algorithm. We initialize two variables, up and down, both set to 1. These will keep track of the lengths of the longest wiggle subsequences ending in an upward or downward wiggle, respectively. Now, as we iterate through the array, we compare each number with the previous one. For I equals 1, we see that nums 1 equals 7 is greater than nums 0 equals 1, which forms an upward wiggle. To account for this, we update up to down plus 1, resulting in up equals 2 and down equals 1. Next, for I equals 2, nums 2 equals 4 is less than nums 1 equals 7, which forms a downward wiggle. This updates down to up plus 1, giving us up equals 2 and down equals 3. Finally, for I equals 3, nums 3 equals 9 is greater than nums 2 equals 4, creating another upward wiggle. This upward wiggle at I equals 3 leads us to update up to down plus 1, resulting in up equals 4 and down equals 3. Moving forward to I equals 4, nums 4 equals 2 is less than nums 3 equals 9, forming a downward wiggle. We then update down to up plus 1, giving us up equals 4 and down equals 5. Finally, at I equals 5, nums 5 equals 5 is greater than nums 4 equals 2, creating another upward wiggle. At this point, we update up to down plus 1, resulting in up equals 6 and down equals 5. Once we finish iterating through the array, we calculate the maximum wiggle subsequence length by taking the maximum of up and down. This gives us max up down equals max 6 5 equals 6. Therefore, the output for this example is 6. Now, let's analyze a new example with the input array nums equals 1, 4, 7, 2, 5. As before, we start by initializing up equals 1 and down equals 1. These variables will help us track the lengths of upward and downward wiggle subsequences. We then iterate through the array, comparing each number with the previous one. At I equals 1, nums 1 equals 4 is greater than nums 0 equals 1, forming an upward wiggle. We update up to down plus 1, resulting in up equals 2 and down equals 1. At I equals 2, nums 2 equals 7 is greater than nums 1 equals 4, but since this continues the upward trend, no wiggle is formed, and the values of up and down remain unchanged. Next, at I equals 3, nums 3 equals 2 is less than nums 2 equals 7, forming a downward wiggle. This downward wiggle at I equals 3 prompts us to update down to up plus 1, resulting in up equals 2 and down equals 3. For the final comparison at I equals 4, nums 4 equals 5 is greater than nums 3 equals 2, forming an upward wiggle. We update up to down plus 1, giving us up equals 4 and down equals 3. After completing the iteration, we calculate the maximum wiggle subsequence length as max up down equals max 4 3 equals 4. Thus, the output for this example is 4. In the final example, we have the input array nums equals 1 1 1 1 1. As always, we start by initializing up equals 1 and down equals 1. Next, we iterate through the array, comparing each number with the previous one. Here, from I equals 1 to I equals 4, all elements are equal, meaning nums I equals nums I1. Since there are no changes in the sequence, no wiggle occurs, and the values of up and down remain unchanged at 1. After completing the iteration, we calculate the maximum wiggle subsequence length as max up down equals max 1 1 equals 1. Therefore, the output for this example is 1. The time complexity of this solution is O(n), where n is the length of the input array nums. To break this down, the algorithm starts by checking if the length of the array is less than 2, which is a constant time operation, O(1). Then, two variables, up and down, are initialized to 1, which also takes constant time. The main work happens in the loop that iterates through the array from index 1 to n1. This loop runs n1 times, and for each iteration, a constant time comparison is made between the current element and the previous one. Depending on the result of these comparisons, one of the variables, either up or down, is updated in O1 time. After the loop, the algorithm calculates the maximum of up and down, which again takes constant time. Since the loop dominates the overall runtime, the total time complexity is O(n). Now, let's discuss the space complexity. The algorithm uses only a few variables and does not rely on extra data structures, so the space complexity is O(1). It uses only two integer variables, up and down, to track the lengths of the longest wiggle subsequences ending in an up or down wiggle. No additional data structures such as arrays or hash maps are used, and the input array nums remains unmodified, with no copies of it being created. In terms of space complexity, the algorithm is very efficient. These variables require constant space, O(1). As a result, the algorithm does not use any auxiliary space that grows with the size of the input. When compared to a brute force approach, the efficiency becomes even more apparent. A naive solution would involve generating all possible subsequences of the input array, which grows exponentially with the size of the array, requiring O(2 to the power of n) space just to store those subsequences. Additionally, the brute force solution's time complexity would be O(2 to the power of n*n), making it highly impractical for large inputs. The optimized solution, on the other hand, processes the array in a single pass and achieves a linear time complexity of O(n), making it far more efficient. When comparing space usage further, the brute force approach not only suffers from exponential time complexity but also requires O(2 to the power of n) space to store all possible subsequences. In contrast, the optimized solution requires only O(1) space, as it uses just two integer variables. This makes the optimized solution significantly more efficient in terms of both time and space. Now, let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, where all elements in the array are either strictly increasing or strictly decreasing, the algorithm still iterates through the entire array, so the time complexity remains O(n). For the average case, with a randomly distributed array, the algorithm still performs a single pass through the array, resulting in O(n) time complexity. Similarly, in the worst case, the algorithm processes all elements, maintaining the same O(n) complexity. To prove the big O mathematically, consider the operations. The initialization steps take O(1), the loop runs n1 iterations, and the final return operation takes O(1). Combining these, the total time complexity is O(1) plus O(n1) plus O(1), which simplifies to O(n). The space complexity is constant, as the algorithm only uses two integer variables, leading to O(1) space usage. When solving the wiggle subsequence problem, there are several common mistakes to watch out for. First, many people confuse subsequences with subarrays. Remember, a subsequence doesn't have to be contiguous, it can skip intermediate elements, whereas subarrays are always contiguous. This misunderstanding can lead to an incorrect solution approach. Another frequent mistake is ignoring edge cases, such as arrays with fewer than two elements or arrays where all elements are the same. For example, cases like an empty array, a single element array, or an array where all values are identical require careful handling to avoid errors. Lastly, overcomplicating the solution is a pitfall to avoid. While some approaches like recursion or backtracking may seem appealing, they often lead to higher time complexity and unnecessary debugging when simpler greedy strategies are more efficient. Another issue to be mindful of is incorrectly transitioning between peaks and valleys in the sequence. This happens when the algorithm doesn't properly update its state as the sequence switches between increasing and decreasing trends, which can break the required wiggle property and lead to invalid subsequences. Additionally, it's crucial to optimize for time complexity. Brute force solutions, which have exponential time complexity, are often too slow for large inputs, such as arrays with 10,000 elements. Instead, leveraging a greedy or dynamic programming approach can achieve linear or near-linear performance, making these methods far more suitable for handling larger datasets. To excel in interviews with this problem, focus on recognizing patterns. Many variations of the wiggle subsequence problem can be solved using either greedy algorithms or dynamic programming, depending on the constraints. For instance, when maximizing the length of the sequence, pay close attention to how transitions between peaks and valleys are handled. Also, take the time to clarify definitions with your interviewer. For example, confirm whether the input is sorted, whether duplicates are allowed, or if there are any additional constraints. If the input size is large, avoid exponential solutions and aim for a time complexity of O(n) or O(n log n). Finally, proactively discuss edge cases. Bring up scenarios like arrays with no wiggle, such as 1, 1, 1, or arrays with only one element, as these can demonstrate your attention to detail and thorough understanding of the problem. Wiggle subsequence is closely related to several other problems that you might encounter. For example, LeetCode 300 focuses on finding the longest increasing subsequence, which is a dynamic programming problem targeting strictly increasing sequences. Another related problem is LeetCode 674, which asks for the longest continuous increasing subsequence, emphasizing contiguous subarrays rather than subsequences. LeetCode 978, the longest turbulent subarray, is also worth exploring. It involves alternating comparisons like the wiggle subsequence problem but is restricted to subarrays. These related problems share overlapping concepts and help build a deeper understanding of sequence-based algorithms. When approaching the wiggle subsequence problem, it's helpful to understand the pros and cons of different strategies. A brute force approach is the simplest to implement and works well for small inputs. However, its exponential time complexity, 2 to the power of n, makes it highly inefficient for larger datasets. Dynamic programming offers a more efficient solution, typically running in n² time. While it's a bit more complex to derive and implement, it provides a structured way to track the longest wiggle subsequence. The most optimal solution is usually the greedy approach, which can achieve n time complexity. This method is perfect for large inputs but requires careful handling of peaks and valleys to ensure the wiggle property is maintained. Each of these approaches has its place, and selecting the right one depends on the input size and constraints. To wrap up, we reviewed the wiggle subsequence problem and its solutions. The optimized greedy approach stood out for its efficiency and simplicity. Remember, understanding edge cases and recognizing patterns is key to mastering such problems. Thanks for tuning in. Like and subscribe for more problem-solving sessions. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!